All right, we are moving on to section 1.2, which is inductive reasoning. The start thinking part says, in his book, How We Believe, Michael Shermer wrote that the human brain is a pattern recognition machine. Patterns help us make sense of our surroundings and make predictions for the future. We naturally seek out structure that allows us to generalize and see relationships. Let's put this into to the test. The first part that the kiddos worked on in class says, can you figure out the missing number in each of the patterns? How would you describe each pattern? So when we're looking at this, you have 31, 27, 23, 19. I mean, technically, it could just be those four numbers repeated again. But when we look at this, I try to figure out, first, am I going over and multiplying or dividing or adding or subtracting by the same number each time? I could see it's going down, so I'd think I'm either dividing or subtracting. And at first, it looks like you subtract 4, and then it's subtract 4, and then it's subtract 4. Okay, so I feel like I do know what this is. I believe that it is subtract 4 each time. So that makes 15, 11, and 7. With the idea, the rule that I think that we have here is just subtract 4 each time. The next one says 2, 6, 5, 15. So it looks like it's add 4, but then it's not add 4 again. It's multiply by 3, but then it's not multiplied by 3 again. So you're going to have to think outside the box and you just start testing things. And this one looks like it is multiply by 3 and then subtract 1 and then multiply by 3 and then subtract 1 and then multiply by 3 and subtract 1, and you can get those. Is that guaranteed the pattern? I don't know, but it's the most likely thing in my mind. The next one the students worked on was a picture pattern shown below. Sketch what would go in the middle to complete the pattern. So when you're looking at this, once again, you're trying to find patterns. So you look at the top one. It looks like one of them has 1 of the shape, then 2, then 3. And some are shaded, some are not. I look all the way at the bottom so that I can start making a generalization. It looks like, once again, it's 1, 2, and 3. It does look like when you're looking at top and bottom, 2 of them will be shaded and 1 of them won't. So then you can look at the middle one and you say, well, it's still missing 3. I just don't know if it's shaded or not. And then we see that there was only 1 of them that was shaded, so this must be shaded as well. So it is 3 of those ovals shaded, and we explain that in there. Once again, the students were working on this in class. Next, it says, last week a friend Jim drank a milkshake at a restaurant and got sick. On Tuesday, he wasn't feeling well after eating cheese. Yesterday, Jim attended an ice cream social and complained of stomach pain. What is the logical conclusion you can make? Give the evidence. My guess is that Jim is lactose intolerant. My evidence would be that every one of the things he ate had lactose in it. It was like a milk product. So that's what most of the students came up with. This logical conclusion, there's a special word for that. It's a conjecture. So when you're looking and you're trying to come up with a rule or just trying to summarize everything here into one rule, that could be called a conjecture. So that's one of our key words. The next one says, what additional piece of information would make you rethink your conclusion? So if you ate tortilla chips and got sick, that would probably not make me rethink Jim ate tortilla chips and felt fine. I want to do something that has to do with milk products. So then we get into this buttery pastry, and one of them says Jim ate a buttery pastry and felt fine. So that would be the one that I would say just didn't make sense because he should be sick. The other one that would kind of make me rethink it, but I didn't circle it, was if he ate tortilla chips and got sick, then I might start thinking that it's not necessarily the milk aspect, but just maybe there's something going wrong with his gut. So, but the main one, since we're kind of zeroing in on the lactose aspect, I think it would be D. The next one says, consider the sequence 8, 4, 2, 1. What do you think the next number in the pattern would be? I think the next number would be 1/2 because it seems like you're dividing by 2 each time, and come up with a different number that fits the pattern, explain your pattern. So once again, if you have 4 numbers, there could be a pattern that those 4 numbers just repeat again. Now, in the fashion of mathematics style notes, you are experiencing something, but we have not really put a name to it yet. A name to any part. We've covered several different things here, but really hadn't put names to it. So the first thing that we're going to put a name to is the concept of inductive reasoning. Inductive reasoning is noticing patterns in data and making a conjecture, or like making some kind of a rule based on that evidence. So if you're looking at individual cases and coming up with a rule, that's inductive reasoning. If you have the rule and you're looking at individual cases, that's something different. We'll talk about that later. But if you have the individual cases and then you come up with the rule, then that is inductive reasoning. And not only that, but the special word for you coming up with your guess at what the data is telling you is it's a conjecture. A conjecture is based off of limited evidence and thus not guaranteed to be true. And that is a big limitation of inductive reasoning. You could see something happen 100 times and it's always the same thing, and you're making a pretty good guess of, when you're using inductive reasoning to think it's going to happen again, but it's not guaranteed because we don't have the rule. We're looking at special cases, and the 101st time it might be different. So you got to be careful when you're trying to use inductive reasoning. It is super beneficial and helpful, but it has its limitations. Next, the students went over and looked at their understanding. So students were looking at this. It was 3 times 5 is 15, 4 times 7 is 28. And you had all these numbers, and you were supposed to come up with a conjecture about an evidence-based conjecture. And what we saw here was it seemed like an odd times an odd was going to be an odd times an even was an even, and an even times an even was an even. Once again, we're looking at limited data here, so this might be true or might not. In math, if you were actually to do this, you would do it differently. Like instead of saying the even number 6, you could say 2n represents all possible even numbers, because 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6. So 2 times n is every single possible even number. But we're not going to be getting into that. My point here is that we are looking at individual cases and trying to come up with a conjecture. So this would be inductive reasoning. The next one, you had a 1 by 1 for figure 1, 2 was 2 by 2, 3 was 3 by 3, and asked what is figure 5 going to look like? And it's probably going to be a square, not guaranteed though, but it might be a square that is a 5 by 5, which has 25 different squares. The next one, students were supposed to look at this and try to figure out what the rule was. I usually go through a process of seeing if am I adding and subtracting or multiplying and dividing by the same number. If that doesn't work, am I adding consecutive numbers? Am I jumping around? Am I multiplying by consecutive numbers? Does it have something to do with the real world? So in this first one, it looks like it's add 1, then add 2, then add 3, then add, no. The next one would have to be add 4, which would have gotten you to 12, and that's not the case. Students were able to find out that this thing was just take the 2 previous terms and add them together. So the 2 and the 3 add to be 5, 3 and 5 make 8, 5 and 8 make 13. This is called Fibonacci sequence, and you actually find it in nature also. But that would be looking at 2 previous terms and doing something to it rather than just 1 previous term. The next one looked like it was add nothing, then add 1, then add 4, then that doesn't make sense. So I go to multiplication. It's not multiplying by the same number, but it looks like it's multiplying by 1, then 2, then 3, then 4, and then it would be 5, 6, 7, and so on. And the last one, since it's letters, it's got to have something to do with like the real world. So looking at this, JFMAM, that is January, February, March, April, May, June, July, August. The next one is Tamara multiplies the number 5 by 2, and the result is bigger. She then gets 5 multiplies by 8, it gets bigger. She uses inductive reasoning to say that anytime you multiply 5 by a number, the result will get bigger. Come up with a, this is another special word, counterexample. It's something that shows that your conjecture was false. So if you multiply by a negative number or a decimal from 0 to 1, it is not going to get bigger. And in math, you only have to find that something doesn't work once to prove that it is false. Proving that it's true is much more challenging, but proving that it's false, you just have to have one case. Now let's take a look at the homework. The first one says, find a counterexample for each one of these. It says adding 2 numbers always creates a number bigger than the added. If you have 2 negative numbers and you add them, the number is getting actually smaller because it's going further into the negative. So that would be your counterexample. Only need one counterexample to prove something is false. The next one, the square root of any number is always going to be smaller. If you do the square root of a fraction, such as 1/4, you end up getting 1/2. So that would be your counterexample. You don't have to show many, you just show one, and that's good enough. If you're proving that it's true, In math, you actually have to look at infinitely many cases. The next one was use inductive reasoning to determine what the next two terms are. The first rule was just multiply by -2 over and over and over. The next one was add 1, then 2, then 3, then 4, and so on. And the next one was just the days of the week. Hopefully that made sense. On the next one, it says 3 plus 4 plus 5 is 3 times 4. 7 plus 8 plus 9 is 3 times 8. 12 plus 13 plus 14 is 3 times 13. And you're supposed to be trying to find out, make a conjecture about what the pattern is. And it seems like it's always going to be 3 times the number that is in the middle. Now, just because it works in these cases doesn't guarantee it's always going to work, but that is our conjecture. The next one, you can see that 3 to the 0 is 1, 3 to the first is 3, 3 to the second is 9, then 27, and then the numbers are getting bigger. And they want to know what is the ones digit of 3 to the 50th. So all we care about is the ones digit. So I kind of zoom in on that, and I see it goes 1397, 1397, 13, and I'm assuming it just keeps going 1397. It's going to rotate through those numbers. So since we started with 0 and we're going to 50, like 3 to the 0 is 1, then we're going to the 50th term. That's actually 51 along the repeated pattern. So how many of the 4 number patterns fit in there? Well, 12 of them, and then you have a remainder of 3. So we don't care about the 12. We're just going to grab our pattern and go to the third number, which is a 9. Some of you guys may have just tried to put 3 to the 50th in your calculator, and your calculator just can't handle it. It's too big of a number. All right, another case of where you could use inductive reasoning. When you're looking at this, this actually happened to me. So I got into stock investing in 2010, 2012, something like that. And this is what I saw. You had it go, the stock market went up, and then in 2000 there was a big dot-com bubble burst, and it tanked, and it went down for several years. And it came back up, and then there was the Great Recession, and then it tanked pretty much to the same exact spot, and it also got pretty much to the same spot for an all-time high. Now in 2013, my question was, what would you do if you were me and you had stock in the stock market and you got to there? If you did what I did, you would sell almost everything because you figure it's going to follow the same pattern. I'll buy back when it's cheaper and I'll make a bunch of money. Well, what ended up happening was I sold in 2013 and it just kept going up and up and up. Let me go ahead and pull up a graph of this. So once again, let's take a look at this. You could see it got to a high, and then they had the dot-com bubble burst, and it went down, and then it went to its high, and then it went down, and then in about 2013, it was back to its high. I sold a bunch. Was that a good idea? Did I use inductive reasoning? Well, no. You could see it just kept going up and up and up and up and up, and I kept waiting. You had these sometimes where it dropped, but for the most part, it has been going up for a very, very, very long time. And lastly, it says your friend missed a lesson today. Explain what inductive reasoning is. So what you should say is you're looking at a set of data and you're trying to find patterns from that data. So you're going to make a conjecture about it by looking for patterns. So it is kind of looking at individual cases and trying to come up with the general rule. It has its limitations because you might be thinking you're seeing patterns that are definitely going to keep going, just like I did with the stock market, and that does not happen in many cases. So there we go, inductive reasoning. The key words would be inductive reasoning. You would need to know what a conjecture is. It's your kind of educated guess. And then a counterexample. If you're trying to prove something is false, you just find one case where it doesn't work, and you can call that a counterexample. Only need one case to show that it does not work. All right, thanks for watching.